Hi guys, IBM is here to solve 9702 paper 22 February March 2022. It's physics 9702 paper 2 AS level structured questions February March. My email is cvia22@gmail.com, and without wasting time I would like to take you to the question paper. So here is the question paper. I will not go through the instructions. Today I want to keep time. It's the paper is February March 2022. 9702. So one student told me I should solve it fully. So without wasting time, you can go through the data given, you can go through the formula and the constants and so on and so forth. Question number 1. A sphere of radius 2.1 millimeter falls with the terminal velocity, that is constant velocity free. That means the resultant force should be 0, because when the velocity becomes constant, the acceleration is 0. So the resultant force, because the resultant force depends on the acceleration. If the acceleration is 0, so the resultant force is 0. Three forces act on the moving sphere: the weight and the upthrust, which is 4.8 times 10 to the power minus 4. The viscous force Fv acting on the sphere is given by Fv is equal to KRV. R is the radius of the sphere, and V is the velocity, and K is a constant. The value of K in SI units is 17. Determine the SI units of K. So these are base units. So Fv is force. We know that the base units of force are going to be, I don't want to put equal signs on base units. So I'll use, I'll say Fv. The base units of force are mass over mass times acceleration, which is kilogram meters per second squared. That is for force. Then K is a constant, R is radius, so the base units of R are meters, and V is velocity. The base units of velocity are going to be meters per second. So I'm going to make K the subject. So K is going to be F subscript V divided by R times V. So which means the units for K will be for F, which is kilogram meters per second squared, divided by R, which is meters, times meters per second. So 1 m was cancelled. So this simplifies to kilogram. So I have S, there's 1 over m becomes per meter. And then I have S power minus 2 divided by S power minus 1, which is S power minus 2 minus negative 1, which is S power minus 1. So this is S power minus 1. So the units are going to be kilogram per meter, S power minus 1. So I avoid equate writing. Here I put equal signs because I was simplifying the units of K. So that's why I put equal signs here. But you notice that previously, when I'm listing the units, I just use these colons. I just use these colons here instead of equal signs. Use the value of the upthrust acting on the sphere to calculate the density rho of the liquid. So we know that upthrust is equal to the weight displaced, which is equal to the density times volume of the liquid displaced, then times G. And of course, we know that the volume is going to be equal to 4 over 3 pi r cubed. That is the volume of a sphere. So they gave us upthrust as 4.8 times 10 to the power of minus 4. So I will simply say 4.8 times 10 to the power of minus 4 is equal to the density of the liquid times the volume, which is 4 over 3 pi. What is the radius? The radius is 2.1 millimeters. So I will say times 2.1 times 10 to the power of minus 3, but this is raised to power 3. So that is volume, then times G, which is 9.81. So I'm just going to make density the subject. So density is going to be equal to 3 times 4.8 times 10 to the power of minus 4 divided by 9.81 times 4 pi into 2.1 times 10 to the power of minus 3, and this is raised to power 3. So 3 times 4.8 exponent minus 4. Then we divide this by, I'll first divide by 9.81 times 4 pi times 4 pi. So I'll open another bracket, 2.1 exponent minus 3. I will raise this to power 3. No, I want this to power 3. What is this? Okay, so my answer was that, divide by, I'm not good at using the calculator, so 9.81 times 4 pi. I can first divide that, then I divide again by the bracket, which is 2.1 exponent minus 3, but this is raised to power 3. Okay, so this is giving me 1.261. 1.261, no. So it's 1,261. So I'll just write 1,261 kilograms per meters cubed. So this is 1,261 kilograms per meters cubed, or if you want, you can write 1,300 kilograms per meters cubed. Okay. On the sphere in the figure, draw 3 arrows to show the direction of the weight, the upthrust, and the viscous force. So since it is moving, of course, the weight acts always downwards. So I'll draw a line from the center going downwards. So this is the weight. Then the upthrust is always upwards. So I'll draw an arrow going upwards. That is upthrust. Because motion is downwards, the viscous drag is upwards. The viscous drag is like friction, which acts in the opposite direction to motion. So I will say the viscous drag Fv is upwards. So Fv is upwards. Those arrows are not drawn to scale. Determine the magnitude of the terminal velocity of the sphere. Okay, magnitude of the terminal velocity. So remember, at constant velocity, the acceleration is constant. The resultant force is 0. And the forces acting downwards, we have only the weight, should be equal to the forces acting upwards, which is the viscous drag Fv plus the upthrust. So we want the magnitude of the terminal velocity of the sphere. Remember, Fv is kr times v, r times speed. That was Fv. So I will say Fv is equal to the weight minus the upthrust. Fv, remember, was k, r times the speed is equal to the weight, which weight was given as, I think, is 7.2 times 10 to the power of minus 4, minus the upthrust was given as 4.8 times 10 to the power of minus 4. So I'm trying to find V. So V is going to be equal to the difference. What is this difference? 7.2 minus 2.5, I think that is 7.2 minus 4.8, I think that is 2.4. So that is 2.4 times 10 to the power of minus 4 divided by K. I think K was given as 17 in the units that we derived. Then R was the radius, which is 2.1 millimeters. So it's 2.1 times 10 to the power of minus 3. I've made V the subject. So I'll just press my calculator. 2.4 exponent minus 4 divided by 17 exponent, 17 times 2.1 exponent minus 3. So this is giving me 0.0067 times 10 to the power of minus 3. So that is 6.7 times 10 to the power of minus 3 meters per second. Water leaves the end of a hose pipe at point P with a horizontal velocity of 6.6 meters per second as shown in the figure. Okay. Point P is at a height h above the ground. The water hits the ground at point Q. The horizontal distance from P to Q is 3.5 meters. Air resistance is negligible. That means acceleration is going to be g, because acceleration is constant when air resistance is negligible. Assume that the water between P and Q consists of non-interacting droplets of water and that the only force acting on each droplet is its weight. Okay, so acceleration is going to be g. Explain briefly why the horizontal component of the velocity of the droplet of water remains constant as it moves from P to Q. So since the only force acting is the weight acts vertically downwards. So that means there's no resultant force. There's no force on the droplet in the horizontal. So the force in the horizontal direction is 0. Force on a droplet in the horizontal direction is 0. If you want, you can say so the acceleration is 0. There is no acceleration in the horizontal, to be precise. So that the time taken for the droplet to move from P to Q is 0.53 meters per 0.53 seconds. So I'll just use equations of motion since acceleration is constant. So S is equal to ut plus a half at squared. I'm considering horizontal motion. Acceleration in the horizontal is 0. When I say ax, it means acceleration in the horizontal or in the x direction. So the distance in the horizontal is 3.5. This is s in the horizontal. Initial velocity in the horizontal was given as 6.6. So I'll say this is equal to 6.6, then times t, of course, plus 0, because acceleration in the horizontal is 0. So t is going to be 3.5 divided by 6.6. 3.5 divided by 6.6, which gives us 0.533030 recurring. So this is 0.530. So as required seconds. Then calculate the height h. Of course, the time is going to be the same, but this time I'm going to consider s in the vertical, which will be initial velocity in the vertical times t plus a half acceleration in the vertical times t squared. The time is the same. Remember, initial velocity in the vertical is 0 because initial motion was in the horizontal. So s in the vertical is h. Initial velocity in the vertical is 0 times t, that is 0 plus a half times g, which is 9.81, then times the time, which is 0.53 squared. Okay, so what is h? I'll just press my calculator. 0.5 for a half, 9.81 times 0.53 squared. So that is 1.377, approximately 1.4. So this is 1.4 meters per second. Sorry, 1.4 meters, not 1.4 meters per second. Then calculate the magnitude of the displacement of the droplet of water that moves from P to Q. Now, displacement is a vector quantity. So displacement is a vector quantity. The horizontal distance here is 3.5. The vertical distance here, we have got it as 1.4 meters. So the displacement is going to be this one here. But before that, I think there is a question above. Yes, for the movement of a droplet from P to Q, state and explain whether the displacement of the droplet is less than, more than, or the same as. It can't be the same. Displacement is a vector quantity. And therefore, it is the straight line distance from the starting point to the finishing point. So let's look here. The displacement is going to be the straight line distance from P to Q, which we notice that it is less than the actual length of the curve. So I'll simply say displacement is the straight line distance from P to Q. So it is less than the distance along the actual path. So the displacement is less than the distance along the actual path. So calculate the displacement. So we have the vertical distance was 1.4 from P, and we have the horizontal distance was 3.5 meters to Q, and the displacement is this one here. So this is the right angle. We just use Pythagoras theorem. 1.4 squared plus 3.5 squared is equal to displacement. So I'll just say displacement is going to be the square root of 3.5 squared plus 1.4 squared using Pythagoras theorem. So 3.5 squared plus 1.4 squared, which gives us, then I find the square root, which is 3.7877, or this is 3.77, or approximately 3. I'll just leave 3.77 meters. Avoid writing answers which are not exact to less than two significant figures. Question 3. A jet of water hits a vertical wall at right angles as shown in the figure. Horizontal jet of water, the density is given, our cross-sectional area is given, the speed is given. Let's say when it hits, it runs down the wall. So let's say as at the point of hitting here, the final velocity will be 0. The velocity here will be 0 at hitting. The water hits the vertical wall with a velocity 5 meters per second. Then, of course, it goes to 0. The velocity rapidly goes to 0. The cross-sectional area is 1.5 times 10 to the power of minus 4. The density of water is 1,000 kilograms per meters cubed. The water runs down the wall after hitting. That means it doesn't rebound or it doesn't continue. Show that over a time of 1.6, the mass of water hitting the wall is 1.2 kilograms. So we know first of all that mass is equal to density times the volume. Which volume of water is hitting the wall here? Volume of water hitting the wall is the cross-sectional area times the length of that water. And of course, we have the cross-sectional area, but we don't have a length. We have the speed and we have the time. So it means L is going to be the speed times T. So this means the volume, first of all, is going to be cross-sectional area times the speed times the time. And the mass, therefore, will be equal to the density times the volume, which is the cross-sectional area, times V, the speed, times T. Okay, so now I'll just substitute the mass. Is going to be the density, which is 1.0 times 10 to the power of 3. Cross-sectional area, which is 1.5 times 10 to the power of minus 4. The speed, which is 5 meters per second. And the time, which is 1.6. So 1 exponent 3 times 1.5 exponent minus 4 times 5 times 1.6, which gives me 1.2 kilograms. Calculate the decrease in the horizontal momentum of the mass of water in air due to heating the wall. Of course, the decrease or change in momentum is going to be the mass times the change in velocity. Since it didn't bound, it just went downwards, so it means the mass is 1.2. The change in velocity can be initial minus final or final minus initial, so I will simply say 5.0 minus 0, which is going to be equal to times 5, which is 6. So this is 6.0. So the change in momentum is 6.0 Newton seconds. The magnitude of the force, of course, we know that force is equal to the rate of change of momentum. So the change in momentum is 6.0 and the time it takes is 1.6. So the time is 1.6. So 6 divided by 1.6, this is 3.75. So this is 3.75 newtons. State and explain the magnitude of the horizontal force exerted on the wall by the water. Of course, now by Newton's third law, the force is going to be equal but opposite. So by Newton's third law, if explain the magnitude of the horizontal force exerted on the wall by the water. So this was the force exerted, the magnitude of the horizontal force exerted on the water by the wall by Newton's third law. By Newton's third law of motion, it means the force is going to be 3.75 newtons because the forces are equal but the opposite. The force exerted by the wall on the water is the same as the force exerted by the water on the wall. So the answer is 3.75 newtons. Then calculate the pressure exerted on the wall by the water. So we know that pressure is equal to force over area. So the force is 3.75. Then the area of this where it hits is 1.5 exponent minus 4. So divide by 1.5 times 10 to the power of minus 4. So divide by 1.5 exponent minus 4. So this is 25,000 or 2.5 times 10 to the power of 2.5 times 10 to the power of 4. This is 25,000 pascals or 2.5 times 10 to the power of 4. Question 4. A child moves down a long slide as shown. The child moves from rest at the top end X of the slide. An average resistive force of 76 newtons opposes the motion of the child as they move to the lower end Y of the slide. The kinetic energy of the child at Y is 300 joules. The decrease in gravitational potential energy of the child as it moves from X to Y is 3,200. This is the decrease in the gravitational potential energy, but the kinetic energy is this. That means if the kinetic energy of the child is not the same as the decrease in potential energy, it means some energy is wasted to overcome resistive force. Determine the ratio kinetic energy of the child at Y when the resistive force is 76, so the kinetic energy is 300, over the kinetic energy of the child at Y if there was no resistive force, then the kinetic energy would be equal the same as the loss in gravitational potential energy. So it means the ratio here is simply going to be 300 joules. That is if there is resistive force over 3,200 joules if there was no resistive force. So 300 divided by 3,200, which is 0.094. 0.094. So that is going to be the ratio here. Use the answer in A to calculate the ratio speed of the child at y when the resistive force is 76 newtons over speed of the child at y if there is no resistive force. So remember, kinetic energy is equal to a half m v squared. It is the same child, meaning the mass is the same. So kinetic energy is directly proportional to the speed squared. So I will call this one 1 and this one 2. Just like I would call this one 1 E1 and this is E2. So let me call this one V1 and the speed here V2. So the ratio V1 over V2. So E1 over E2 was 0.094. So I have two equations here. E1 is equal to a constant times V1 squared. And E2 is going to be the same constant times V2 squared. When I divide, so it means E1 over E2 is equal to V1 over V2. But these are going to be squared. So what does that mean? So the ratio V1 over V2 is going to be the square root of E1 over E2. So this is going to be the square root of 0.094. So I just get the square root of the answer, which is 0.31. Okay, so that is 0.31. Then calculate the length of the slide from X to Y. The length of the slide. So first of all, I need to find the work done against friction. The work done against resistance. And of course, the work done is going to be 3,200 minus 300, which is going to be 3,200 minus 300. That is 2,900. So that's the work done against resistance or friction. And also we know that work done is equal to force times distance. So we want the distance in this case. So the work done is against friction is 2,900. The frictional force was 76 times the distance which you want. So the distance is going to be that one divided by 76, which is 38.2 meters, or approximately 38. At the end Y of the slide, the child is brought to rest by a board, as shown in the figure. So it means he reaches the board with kinetic energy of 300 joules. And then this kinetic energy decreases. At this point here, kinetic energy becomes zero. That means the child now gains elastic potential energy. Okay, so a spring connects the board to a fixed point. The spring obeys Hooke's law and has a spring constant of 63 newtons per meter. The child hits the board so that it moves to the right and compresses the spring. The speed of the child becomes zero. So it means all the kinetic energy is lost when the elastic potential energy of the spring has increased to its maximum value of 140 joules. Okay, so calculate the maximum compression. Calculate the maximum compression of the spring. So we know that elastic potential energy is a half k x squared. So the energy is 140. So this is going to be a half, which is 0.5. They gave us k as 63, then times x squared. So what is x? X is going to be the square root of 140 divided by 0.5 times 63. 140 divided by 0.5 times 63 square root. So that is 2.5. 1. So x is 2.1 or 2.11 if you want. X is 2.11 meters or 2.1. So this is 2.11 meters. If you want, you can first find f. From f is equal to kx. Remember, k is 63, so this will be 63 x. Then you use energy is equal to a half Ka, a half Fx, which will be a half times F, which is 63, again times x. So it becomes, so 63x times x, which becomes 0.563 x squared times 63x squared. Then we equate this to 140. It is the same thing here. So this is another way of approaching it, but it gives the same answer. Then calculate the percentage efficiency of the transfer of the kinetic energy of the charge to the elastic potential energy. Remember, the kinetic energy was 300 joules. What became potential energy is 140. So we can say efficiency, percentage efficiency is equal to the energy output over the energy input times 100. The energy output is 140. The energy input was the kinetic energy times 100. So 140 divided by 300 times 100, which gives us 46.6 recurring, which is approximately 47%. The maximum compression of the spring is x naught. So that means the maximum elastic potential energy must be at x naught. Maximum elastic potential energy. So the graph should stop at x naught. Sketch a graph to show the variation of the elastic potential energy of the spring when its compression x from x equals to 0 to x equals to x naught. So the compression increases. Now that is a confusing part to a student. The compression increases. So the elastic potential energy is a half kx squared. So it means elastic potential energy is directly proportional to x squared. If we check values, it means E is maximum when x is maximum. When x equals to 0, E is automatically going to be 0. You can check if x equals to 1, E is equal to a constant times 1. When x equals to 2, E is equal to a constant times 2. But when x equals, sorry, this is a constant times 4. When x equals to 3, E becomes a constant times 9. So you notice that E is increasing more rapidly than x. So that is a curve of increasing gradient. So your graph should be a curve of increasing gradient. So it's a curve of increasing gradient, which touches the vertical line at that point. Okay. Then question 5, state the conditions required for the formation of a stationary wave. Of course, a stationary wave must have two waves of the same type, having the same frequency or wavelength, traveling at the same speed in same opposite directions, and they should overlap or meet at a point. So we must have two waves of the same type. Two waves of the same type having the same frequency or wavelength, traveling at the same speed in opposite directions. So they overlap at a point or meet at a point. So if they meet at a point, then they will form a stationary wave. State the phase difference between two vibrating particles in a stationary wave between two adjacent nodes. So of course, if this is a node and this is a node, particles between two adjacent nodes always vibrate in phase, but they will vibrate out of phase with the particles in the next segment. So all particles here vibrate in phase with each other. So between two nodes, the phase difference is zero. But between a node, an antinode, and another antinode, particles in one segment are always 180 degrees out of phase with particles in the neighboring segment. So for this particular question, between a node and another node, the phase difference is zero because particles are always in phase. A motorcycle is traveling at 13 meters per second along a straight road. The rider of the motorcycle sees a pedestrian standing in the road directly ahead and operates a horn to emit a warning sound. So the pedestrian or the observer is standing in front. So it means the motorcycle is approaching. The pedestrian hears the warning sound from the horn at a frequency of 543 Hz. The speed of the sound in the air is 330 meters per second. Calculate the frequency to three significant figures of the sound emitted by the horn. So it's to three significant figures. So the observed frequency is going to be V over V because it is moving towards. So this will be minus so that the frequency is higher times the frequency of the source. So the observed frequency is 543. The speed is 334 for sound over 334 minus the speed of the source, which is 13, then times the frequency of the source. So just I'll just press my calculator. I'm making Fs the subject, which is going to be 543 into 334 minus 13 divided by 334. So 543 times 334 minus 13 divided by 334. So that is 521.8, which is approximately 522 because they want three significant figures. So that is 522 Hertz. The motorcycle rider passes the stationary pedestrian and then moves directly away. Is moving directly away from her. As the rider moves away, he operates the horn for a second time. The pedestrian now hears the sound that is increasing in frequency. So the sound is increasing in frequency, yet we expect that if the motorcycle is or the source is moving away, we expect the frequency to be going down. But if the frequency is going up, then the speed must be changing. So we look at F naught equals to V over V. Because it's moving away, this is supposed to be plus Vs divided by, times Fs. But the frequency is increasing. The only way the frequency should be increasing must be because Fs is constant, of course. Speed in sound in air is constant. The only thing which must be changing is the speed of the source. So the speed of the source must be, because the frequency is increasing, the speed of the source must be decreasing to make the numerator smaller so that the observed frequency is higher. So state the variation, if any, in the speed of the motorcycle when the rider operates the horn for the second time. So the speed Vs must be decreasing to make the denominator V plus Vs to become smaller so that F naught to be higher. So it means the speed is decreasing. So the speed is decreasing. Okay. A beam of vertically polarized monochromatic light is incident normally on a polarizing filter as shown in the figure. Okay. Vertically polarized incident light beam, intensity I naught is incident on that. The angle between the vertical and the axis of transmission is 20. The filter is positioned with its transmission axis at an angle of 20 degrees to the vertical. The incident light has intensity I naught. The transmitted light has intensity IT. By considering the ratio IT over I naught, calculate the ratio amplitude of transmitted light over amplitude of the incident light. Show your work. Okay. So number one, we know that intensity, transmitted intensity IT is equal to incident intensity I naught cos squared theta, which means transmitted intensity IT over the incident I naught is equal to cos squared of 20. That's one equation. We also know that intensity is directly proportional to amplitude squared. So uh, if we say the incident intensity is A naught and the transmitted intensity is AT, so we shall say intensity transmitted is equal to a constant times amplitude AT squared. Then incident intensity is equal to a constant times incident amplitude A naught squared. I'm going to divide the two equations again. So it means intensity transmitted over the incident intensity is equal to K cancels out, so I remain with AT over A naught, and the whole of this is squared. So I'm now going to combine the two equations. So the amplitude transmitted over the incident intensity, but this is squared, is equal to cos squared of 20. So I will get the square root. So the ratio in amplitude transmitted over incident intensity is going to be the square root of cos squared of 20, which is the same as just cos of 20. So I'm getting cos of 20, which is 0.94. This is 0.94. So that is the ratio. The filter is now rotated about the direction of the light beam from its starting position shown in the figure. The direction of rotation is such that the angle of the transmission axis to the vertical initially increases. Okay, the angle initially increases. Let's check. Coming here. So this angle, if it means it's going like this, so that the angle increases. So if this angle increases, it is by the time the intensity goes to 0, it must have gone through 70 degrees. So the intensity decreases, but as the angle from the vertical increases. So by the time here, along this intensity goes to 0, transmitted intensity becomes 0. Then if we continue rotating the axis so that now it is here, if this was here, transmitted intensity will be 0. So it means after the horizontal, now the transmitted intensity starts increasing. Of course, the rate at which it decreases should be the same as the rate at which it increases. So when it is here, when it goes through another 70 degrees, now the intensity goes back to its original value. So let's see the equation. Let's see the question here. Calculate the minimum angle through which the filter must be rotated so that the intensity on the transmitted light returns to the value that it had when the filter was at its starting position. So if the filter was at this position here and the intensity was IT, so it decreases when we rotate it through further 70 degrees, it goes to 0. Then it means when we rotate it through another further 70 degrees, it increases back to the original value. So we shall have rotated it through 70 plus 70, which is 140 degrees. So the angle here is going to be 70 plus 70, which is going to be 140 degrees. Question 6 is electricity. I think electricity is easy. The ends of a metal resistance wire are connected to a battery of EMF 8 volts and negligible internal resistance as shown. The power dissipated by the resistance wire is 36 watts. Calculate the current in the resistance wires. Of course, we know power is IV. So the current is going to be the power, which is 36 divided by V, which is 8. So 36 divided by 8, that is 4.5 amperes. the number of free electrons that pass through the resistance wire in a time of 50 seconds. So charge is equal to current times time. Remember, charge is number of electrons in a conductor times the charge of each charge carrier. So we want the number of electrons, which will be I times T divided by E. So this is going to be 4.5 times 50 divided by the charge of each electron, which is 1.6 times 10 to the power of negative 19. So 4.5 times 50 divided by 1.6 exponent minus 19. So this is giving me a 1.41 times 10 to the power of 21. 1.41 times 10 to the power of 21. The resistance of the wire. So we want to find the resistance. Remember we said power. We know power is also V squared over R. And we want to find the resistance. So I can say resistance is going to be V squared divided by the power, which could be V. I think V was 8.0 squared divided by the power, which was 36. 8 squared divided by 36, which is 1.7777, which is 1.8. So this is 1.8. Alternatively, I could use resistance is equal to V over I. V was 8.0 and I was 4.5. I think the answer is the same. Alternatively, I could use resistance is equal to power divided by I squared. Power was given as I think 36 and we got the current as 4.5, so I would say 4.5 squared. I think the answer is the same. The metal of the resistance wire in the circuit has resistance 1.4 times 10 to the power of minus 6 ohm meters. The cross-sectional area of the wire is 0.25 millimeters squared. Determine the length of the wire. So we know that resistance is equal to rho L over cross-sectional area. We want L. So it means L is going to be R times A divided by rho. So L is going to be R. What is R? R was 1.8. Okay. 1.8. Cross-sectional area. I have to change from millimeters squared to meters. So this one, because 1 meter is 1,000 millimeters, it means change from millimeters squared to meters. I'll multiply it by 10 power negative 6. So this will be 0.25 times 10 to the power of minus 6. Remember, I have to square both sides. That's why it is power minus 6. Okay, so that is the area. Then divide by the resistivity, which is 1.4 times 10 to the power of minus 6. Minus 6 has cancelled. I'll just say 1.8 times 0.25 divided by 1.4, which is 0.32. So I'll just write 0.32 meters. The circuit shown in the figure is modified by replacing the original resistance wire with the second resistance wire. The second resistance wire has a greater diameter, so diameter is greater diameter than the first one. So that means the cross-sectional area is increased. There are no other differences between the second wire and the original. So it means resistivity is the same, the length is the same. Okay. By reference to resistance, state and explain whether the power dissipated by the second wire is more than, less than, or the same by reference to resistance. So remember, the power is going to be equal to I squared times R. The PD, the PD is going to be the same because it is still across the same power supply. But the current is going to, of course, let's first check resistance is going to be rho L over area. There's a greater area, which means the resistance has decreased. So greater diameter Greater diameter means larger cross-sectional area. Which means the resistance is less. So the resistance is less. So the resistance is less. And if the resistance is less, so it means for the same PD, there will be more current. If the PD is the same, then the current is going to be higher. So for the same PD, there will be more current. For the same P, there will be more current. Whether I use power is equal to I squared R or I use power is equal to IV, here, for the same P, the current is greater, the power is greater. Here, when the current is greater, remember it is also squared, still the power will be greater even if the resistance is smaller. So for the same P, there will be more current. So from power equals to, let me just use IV. From power is equal to IV, the power dissipated is more. More power. I think I'm tired. More power is dissipated. Okay. So we are saying because the cross-sectional area was increased, the resistance is smaller. If the resistance is smaller, for the same PD, the current is greater. And from power is equal to IV, for the same PD, that is for if V is constant, the current has increased, so the power dissipated has increased. Even if I use power is equal to I squared R, remember R has decreased, but the current is squared. So, and here the current has increased, but it is again squared, so the power is again going to be increased. The circuit shown in the figure is modified by connecting a second battery of EMF 80 volts and a negligible internal resistance. So we have two batteries in parallel with the original battery and the original resistance wire as shown. So with the original resistance wire. By reference to the current in this resistance wire, state and explain whether the addition of the second battery causes the power in the original resistance wire to decrease, increase, or stay. Of course, it's going to stay. The current is going to stay the same because the total, the PD or the EMF, the PD across the original wire is still going to be 8. When we have two batteries in parallel, it's only the PD across the device is equivalent to the PD across the EMF of just one cell. So it means the current in the wire is the same. Since the PD across the wire is the same, it is still 80 volts. It's not 8 plus 8. So the PD across the wire is still the same. That is 8.0 volts. What is the implication? The current in the wire is going to be the same. The current in the wire is the same. And if the current in the wire is the same, remember power is equal to IV. So the power stays the same. Because remember power is going to be I times V. When you have batteries in parallel, the PD across the device is the same as the EMF of just one battery or one cell. So the current will be the same. So from power is equal to IV, the power stays the same. A nucleus of sodium 22 decays by emitting a beta plus. A different nucleus is formed by the decay. State the name of another lepton that is produced by the decay. So whenever beta plus particle is emitted, this is an antiparticle. It is accompanied by a particle which is mostly a neutrino. So the particle here is called the electron neutrino. If it was beta minus, it would be antineutrino, antineutrino. So this is electron neutrino. Okay, it's the electron neutrino which accompanies the beta plus. Determine the nucleon number and the proton number of the nucleus that is formed by the decay. So the nucleus is sodium, which is 2211, which is decaying to give us beta plus, which is beta 01 plus a new nucleus X. Let's balance. Nucleon number remains 22. So to balance, this should be 10. So that 10 plus 1 is 11, and the other side we have 11. So determine the nucleon number and proton number of the nucleus that is formed. So proton number is 10, nucleon number is 22. The quark composition of a nucleon in the sodium nucleus is changed during the decay. Describe the change to the quark composition. So there has been loss of a proton. So a proton has been lost. So in other words, a proton must have changed into a neutron. So if a proton is changed into a neutron, it means up, up, down changes to up, down, down. So we can simply say up, up, down changes to up, down, down. Or you can just write up, up, down changes, up, up, down changes to up, down, down. That is fine. Or you can simply say an up quark changes to a down quark. Any of those. And lastly, we still have more. A baryon consists of quarks. Remember, baryons are made up of 3 quarks. The charge of the baryon is minus 2e. Remember, they have the same flavor or same type. They have the same type, so they are identical. The charge of the baryon is minus 2e, where E is the elementary charge. Calculate in terms of E the charge of each quark. So a baryon is made up of 3 quarks. A baryon is made up of 3 quarks. So let the charge of each quark be Q. So I'll say 3 times Q should give us minus 2e. So which means the charge of each quark is minus 2 over 3 times E. So this is minus 2 over 3e. And this is either, remember up is 2 over 3e. That is up. So ant up will be negative. And then top is 2 over 3e. So ant top is negative. Then charm is 2 over 3e. So ant charm is negative. So we can have ant up, or we can have ant top, or we can have ant charm. Of course, in an exam, just write one of them. And I think that is the end of this simple paper. Until next time, bye bye.